Hello everyone, welcome to lecture 26. So starting today we're going to move on to waves, which is chapter 15. The next two lectures, 26 and 27, will be chapter 15. We're going to cover everything about waves. And then our last lecture of the class will be on sound waves. So very similar, but slightly different material there. All right, so let's start by thinking a little bit about what are waves. And the big thing that I like to emphasize when it comes to waves is that you already really know what waves are. Again, in the same way you already kind of know how periodic oscillations work or angular movement works, you know what waves are. And a lot of my goal for you is simply to put a little math behind what you already know. So, you are all very familiar with one example of a wave, namely the wave that you do at sporting events. All right, so here is an artist's illustration of the wave that we do at sporting events. Again, I'm very sorry we can't all be in class because this is one of the demos I love to do. We'd be doing the wave in class. But since we can't do that live, let me just show you. So this is some British soccer game. It's I guess it's Champions League. And if you look towards the back, you can see there's this wall of people right? And towards the back, you see there's this wall of people see that wave. And in a couple of seconds, it's going to come. There you go. The wave passes along, and it continues around. See the wave as it moves through the stadium. So kind of left along the wave is moving across the stadium. And that turns out to be a very good example of what's called a wave or a wave pulse. And the reason I want to keep coming back to this type of wave is that we can learn actually a lot about how waves work from this one example. So question number 1 is, which direction did you move if you were part of the wave? All right, so I want everyone to kind of pretend that you're doing the wave. It's coming from your left. You stand up, and you sit back down. Let me see if I can do this on camera. All right, so I'm in a sports stadium. A wave's coming from this side. I'm watching. It'll come up to me. I do this, right? So question number 1, you are a particle in that wave. Do you move up and down or left and right? You move up and down. So that's really important. In this particular type of wave, each particle moves vertically, but does not move horizontally. Now, question number 2, what direction does the wave move? Does the wave move vertically or horizontally? And here it's pretty obvious from the YouTube video. I'm just going to watch the same YouTube video. Which direction is that wave moving? Vertical or horizontal? Clearly, it's moving from left to right across the screen. It's moving horizontally. So the particles move up and down vertically. The wave itself moves horizontally, not vertically. And similarly, if I looked at the energy in the wave, let's go back to our YouTube video. So right here, where I paused it, the wave is roughly in the center of the screen. Everyone sees the wave is in the center of the screen and it's moving across. So the question is, who here has energy? Who here has kinetic energy? Is it the people way off to the side of the wave? Or when I do the wave, do I have kinetic energy when I'm watching, waiting for it to come to me, or when I do this? When I do this, right? So the the energy is also moving along with the wave. It's going from left to right, or right to left in the YouTube example. So the wave moves horizontally, energy moves horizontally, but the particles in the wave move vertically. And the last bit, which is not as true of sporting events, but ideally true, is that the wave will maintain its shape as a function of time. So as it moves along, it's going to keep a similar shape as it goes. All right, so now let's take that exact same example and put it on a string. So there are three major types of waves we're going to talk about. The one we just talked about is what's called a transverse wave. So that's the case where the particles themselves are going to move up and down. So you can think of those particles as students doing the wave. And the wave is going to move right to left horizontally. A good example of this is a slinky.
New Chips Ahoy cookies made with Hershey's milk chocolate.
I'm not advertising Chips Ahoy. I apologize. I thought it had already skipped.
Hi guys, today I just want to show you a demonstration of
example,
transverse and longitudinal waves using a
full screen, that's fine. We go to about 50 seconds. And the advantages of slinkies is they can actually do all of the different types of waves, or at least
is moving
so here is an example of a
perpendicular to the direction.
The wave is going to move left to right on the screen.
Now another kind of wave is a longitudinal wave.
Moving up and down. So this is identical to the wave at a sporting event that we just talked about. Another option is what's called a longitudinal wave. That is where the particles move parallel to the wave instead of perpendicular to the wave. So that's pretty easy to see on a slinky at about 118 in this video. So here I have my slinky, which is just like an ideal spring.
Longitudinal wave.
Amazing. If I send these little pulses, it's going to compress on the spring. For those of you following along at home, there's another way I can do that. So imagine at the sporting event, instead of standing up and down, I look, and when it comes, I'm going to do a little cheerleader. I'm going to do this, okay? So I start out with my particles like this, and I'm going to, as it comes past me, do a little hula dance. That is a longitudinal wave. And again, my particles move horizontally, but my waves move way differently. They move, my wave, it moves all the way across. And so an important thing in all waves, the particles, the students in my wave, they're going to move a little bit up and down, a little bit side to side. They're not going to jump and run across the room. So the wave is going to move all the way across the room. The individual particles don't really move very far. They do a little bit here or a little bit there. So that's going to be a really key thing to remember. And finally, before we start to describe that mathematically, I simply want to mention there's another related type of wave called a surface wave. Here the particles move in little circles near the surface, so it's kind of got a little longitudinal component, a little transverse component, but the big thing there is it's happening on the surface. We won't talk so much about surface waves, but just be aware that also can be described in the same language as what we'll talk about in this class. All right, so the big thing to remember with waves is that they are disturbances of the medium. So let's say I have a piece of string or a slinky. The slinky itself in equilibrium is just going to kind of sit there. But what's going to happen when I want to do a wave is I'm going to shake it a little bit up and down. And then that disturbance, that shaking from the equilibrium is going to move along. So the disturbance itself, the wave, moves along to the right. The particles are not the wave. They're just the particles on the string. They'll move up and down. And that's what we mean when we talk about these transverse waves. The disturbance propagates at a definite speed in a definite direction, in this case to the right, but the medium itself, in this case the string, is not transported, just the disturbance. And as I will keep coming back to and we'll talk a lot about next time, waves do transport energy. All right, so a bit of terminology here. If I have a single wave like what's shown here, it's called a pulse. So if we go back to our slinky example, the examples they were showing are what are wave pulses. So they're going to take their slinky, they're going to stretch it out, and they're going to send, there we go, individual pulses.
So you can see the pulses or the waves are moving from the left to the right.
Okay, so here we go. He's going to send.
So the energy is moving from the left to the right, but the actual slinky itself is moving perpendicular to the direction.
One pulse, two pulse, etc.
Now another kind of wave is a longitudinal wave.
Other option.
Let me give this a go.
I can send what's called a traveling wave. And if you look at that little demo right there,
so you can see
the entire spring.
So you can see the pulse
seems to continue to go to the right, continues to travel at a finite velocity. So that's what's called a traveling wave. And for the most part in this class, we're going to talk about traveling waves. So if we talk about traveling waves, we'll start now. First thing we need to know is how to describe it mathematically. So we can actually guess an answer and it will turn out to be right, but we can kind of logic through this a little bit. So the way we're going to generate a traveling wave is we'll have some mass on a spring, for example, that's just going to shake the end of that string up and down. And what will happen is that will cause a wave to go along. That wave, that disturbance, will move to the right. And if I plot out little pictures of this, little snapshots at t equals 0, let's say this x equals 0 is maximally displaced, and then my pivot here, my generator, is going to go up and down. What will happen is the wave will appear to move to the right. So if I track, for example, the bottom of this potential, after a little bit of time, the bottom will move to the right, and it'll keep moving to the right until eventually it comes back to the next place where that was a minimum. Okay, so on this drawing, on this set of snapshots, I can see two different things. One is that if I take a look at, for example, my y equals 0 point, it starts out at maximal, it goes down, goes negative, comes all the way back up, and eventually comes back. So at a given point on the string, it looks like a simple harmonic oscillator, and that means it's characterized by a period, capital T. Secondly, if I look at the string itself at a particular point in time, you'll notice that also looks like a sinusoid. So for example, it starts out minimum, goes maximum, and then comes back. The distance between one of these maximums and the next one, or one of these minima and the next one, is called the wavelength, and we denote that by the Greek letter lambda. So the wavelength tells us how far it goes before it becomes spatially periodic. That's the distance in space. And the t, the period, tells us the distance in time to go from one peak to the other peak. All right, so now again, if we put this in the language of math, at each position x, y moves up and down with a simple harmonic oscillator. So that tells us that at a given value of x, I simply have to follow the harmonic motion equation. Y is equal to a cosine omega t plus phi. So at any point x, I have a simple harmonic oscillator. Similarly, at any point in time, I have a simple harmonic oscillator in space. So a cosine 2 pi x over lambda plus phi looks very similar to the previous one, but now instead of omega t, I have 2 pi x divided by lambda. And here I've chosen this because if x goes to x plus 2 pi over plus lambda, I just shift by a multiple of 2 pi. In other words, nothing happens. So this guy is going to repeat itself with the wavelength equal to this lambda. So those are two things it has to do. The other one is that the wave has a velocity. So if you look at what the velocity means, it means that after I start at t equals 0 and end at t equal to capital T, so after one period, that wave had better have moved one wavelength to the right. It comes back to itself, but it's shifted by one wavelength. And that's my wave velocity, meaning my velocity is how far it's moved, lambda, divided by how long this takes, capital T. So those are the three pieces that we need in order for it to work. And the way we're going to solve all three of these equations is by the following, through all three of these rules, is by the following equation. Y is equal to a cosine omega t minus 2 pi x divided by lambda. And then if you want to, you could add a phase to this. So it could be omega t minus 2 pi x over lambda plus some arbitrary phase. We're going to stick to this. We're going to set the phase equal to 0 for most of the work, just to make our lives a little bit easier. Okay, so let's quickly check that this works. That's my guess. Let's check that this guess makes sense. So statement number one that I told you is that at t equals 0, x equals 0, I had a simple harmonic oscillator. So let's go ahead and plug in x equals 0 into this equation. That cancels out the second term. I get a cosine omega t, and aha, that's a simple harmonic oscillator. So we're good to go on that one. Secondly, at any constant time, the result is a cosine dependence in space. So again, let's plug in a constant time. That means omega t is a constant. And what I get is a cosine constant minus 2 pi x over lambda. But now I can play around with this a little bit. For example, cosine is an even function, meaning I can flip both of these signs from negative positive to positive negative. I multiply both by -1. I get cosine of 2 pi x over lambda plus some constant, which I will call the phase phi. So at constant t, indeed, I get this solution for my y. Y is 2 pi x over lambda plus phi. And finally, we need to check that this wave has the appropriate velocity. Okay? So let's go ahead and check that. This one we have to do a teeny bit more math on, so we're going to go ahead and play around with this expression and show that the wave is going to travel to the right with a velocity lambda divided by capital T. So wave velocity. Again, the wave equation that I guessed is that my displacement y, so y, remember, is how this particle moves up and down as a function of x and t, is going to be a cosine 2 pi x over lambda minus omega t. I think on the slides I may have written this the other way around. Omega t minus 2 pi x divided by lambda. Those are both the same thing because cosine of x is equal to cosine of negative x. It's an even function. Okay, so these guys are the same thing. We'll go ahead and use, I don't know, the second one, doesn't really matter. And we're going to go ahead and plot this guy out. Okay, so again, as before, let's plot it out for some particular space and time. I'll plot it out as a function of space. It's some sort of cosine that looks like this, right? So the peak to the next peak, that distance is lambda. And this value, y at x equals 0, is just a cosine omega t, because I plug in x equals 0 into that equation. Okay, so whatever time I've chosen, that's what's going to set my y at x equals 0. Rightio. So this is what our function is going to look like. Now, if I take a look at the maximum, so what properties can you tell me about this phase, which we'll call capital phi, at the maximum value? So where does the cosine return its maximum value? Well, that phase had better be 0, or 2 pi, or 4 pi, etc. We'll pick phi equals 0, it doesn't really matter. That's going to be the position of the peak. So in particular, let's track what happens at one of these peaks, where y, the displacement of the individual particles, is as large as possible. Okay, so I told you that the phase, phi, is omega t minus 2 pi x divided by lambda. And now I'm telling you that we're going to track what happens when that phase is equal to 0, when I'm at the peak of the displacement. So what we can do is we can solve for x as a function of t. What I'm going to do, I'm going to start by bringing this 2 pi x over lambda over to the other side. So 2 pi x divided by lambda is equal to omega times t. I'm going to multiply by lambda, divide through by 2 pi. So x is equal to omega lambda over 2 pi times t. And now I'm going to do one more thing. I'm going to do a substitution of our period. So just like simple harmonic oscillators, there's a relationship between omega and period. Omega is 2 pi divided by the period, same as the simple harmonic oscillator. You'll notice actually the time dependence of waves is the same as simple harmonic oscillators. And so if I plug that in, x is equal to omega, 2 pi divided by t, times lambda divided by 2 pi, all times lowercase t, Or in other words, my 2 pi's cancel. I get lambda divided by period times little t. So the position of the peak is proportional to time. Position is proportional to time. And we know if x is proportional to t, the relationship is the velocity, right? So position is velocity times time for something that moves with a constant velocity. So we can identify lambda over t here as the wave velocity. That's the velocity at which this disturbance, the wave, propagates through the material. Okay, so now we have completed all of the check marks, and now we can conclude that this equation, y of xt is equal to a cosine omega t minus 2 pi x over lambda, is a good description of the traveling wave. So this solution is important. It goes by a name. It is called the wave function, the function that describes the wave. And the key point that you should remember is that what this equation tells us is the y position of each particle. So for example, this particle right here, sitting at x is equal to whatever that x value is, I guess lambda over 2. It's telling us the y position of that particle as a function of time. Or equivalently, it's telling us the entire wave, y, of x at any point in time. So it describes the position of every single particle in the wave at any given point in time. In other words, it tells us everything. All right, so that was for a usual wave that travels to the right. One thing you can easily check is that if I simply reverse the sign, omega t plus 2 pi x over lambda, that reverses my velocity. So if I come back to this derivation, let me just quickly redo the derivation with a positive sign. So now for a left moving wave, the phase, that thing sitting in the cosine, is, one second, omega t plus 2 pi x over lambda. And as before, let's just track what happens when the phase is 0, that first peak. So we'll solve this guy for x. We get x is equal to now negative 2 pi, negative lambda omega over 2 pi times t. You again substitute omega is 2 pi over t. This becomes negative lambda divided by t times time. In other words, the velocity is now negative because it's moving to the left. All right, so if you want to go from a right moving wave to a left moving wave, all you got to do is change the sign of that term in here. Great. One second. Let's go ahead and go to the next side. Okay, so that's the wave equation. Now in that wave equation, there were a few different variables that I defined. We kind of want to discuss what they mean. So 3 of them are very similar to what we've seen before. Amplitude A is how big the wave is. And just like a simple harmonic oscillator, that's set by the initial conditions that I have. If I shake it really hard, my amplitude's big. If I shake it not that hard, my amplitude is small. The oscillation period, T, entered into that wave equation. I actually wrote it in the language of omega, but remember omega is 2 pi over t, frequency is 1 over t, so they're all kind of describing the same thing. Now, one big difference is that unlike the harmonic oscillator, period is now going to be set by initial conditions. So for a traveling wave, oscillation period is set by how fast I shake it. If I have a slinky and I shake it very fast, the period will be short. If I shake it very slow, the period will be long. So that's not a fundamental constant of nature, it's just set by how fast I go. Similarly, the wavelength lambda is set by how fast I shake it, or by the initial conditions. So wavelength, remember, is if I take a picture of the wave at any given time, so I take a picture, plot my displacement of those particles y as a function of x, the position of the particles. Lambda is simply telling me the distance between one peak and another. That again is set by the initial conditions. So one quick thing before we move on, I'm going to define an object called the wave number, which I'm going to denote by k. So k is simply defined as 2 pi over lambda. And notice, k plays the role of omega except for space. So omega is 2 pi divided by t, meaning that I always have expressions of the form cosine omega t. K is 2 pi over lambda. And when you plug that in, what you'll find is I'm always going to get expressions of the form cosine k times x. So just like with simple harmonic oscillators, always try to convert into wave number k first, and then work with the problem. It's much easier to work with than lambda. All right, so these are all the things that are set by initial conditions. The fundamental physics enters into that wave velocity, v. That, as we will see, is set by the physical constants in our system. We don't get any control over that, or set by the physics anyways. So the velocity, as we saw, was lambda over t. We had lambda is equal to 2 pi divided by k, and we had period t is equal to 2 pi divided by omega. So if I plug those in, velocity is equal to lambda over t, which is 2 pi divided by k over 2 pi divided by omega. You see that velocity can also be written as omega divided by k. So that's another useful rewriting of the velocity. And finally, just to quickly say, there are multiple different ways I can write this exact same wave equation, and sometimes one will be more useful than the other. So we've seen one way on the previous slide. Another option is a cosine 2 pi x over lambda minus t over capital T. Another way is a cosine k of x minus v times t. Here that velocity is pretty apparent because x minus v times t is like how fast it's going. And the big one, the one that I'm going to keep coming back to, is a cosine kx minus a omega times t. So if in doubt, the best way to write the wave equation is a cosine kx minus omega t. But you will need to go back and forth between these choices. All right, so that's enough explaining. Let's go ahead and start practicing with an example. So imagine I create a traveling wave on a spring, and its wave function is given by y, the displacement of any given point in the vertical direction, equal to a cosine kx minus omega t, or equivalently omega t minus kx. The amplitude a is 0.12 centimeters, omega is 9.1 radians per second, k is 11 inverse meters. And I've shown you a picture at t equals 0. So what I want you to do based on this is figure out the wavelength, figure out for the snapshot, I've shown you which particle is moving fastest, where is the wave velocity largest, and how long is it going to take for point 8 to go back down and come all the way back up again. All right, very good. So hopefully you've had a chance to do this. Let's go ahead and go over this answer together. 1 second. All right, so first off, what is the wavelength lambda? Well, we're given quite a bit of information. We're given the whole wave equation, a cosine omega t minus kx, which again tells us everything. We are given that a is whatever it was. Give me 1 second here. 0.12 centimeters. or since we like our SI units, amplitude is 0.0012 meters. Omega is 9.1 radians per second, or just inverse seconds, and K is 11 inverse meters. So part A of the problem, what's the wavelength? That's pretty straightforward. The wavelength, lambda, is just 2 pi divided by K. When I plug in some values, that turns out to be 0.5712 meters. All right, so now let's ask a little bit of conceptual questions. Here I've taken a picture of this wave at t equals 0. And the question is, at t equals 0, which point is moving fastest? Point 1, point 2, point 3, 4, etc., all the way up to 11. Okay, so mentally take a vote. Which points do you think are moving fastest? And the answer is going to turn out to be 2, 6, and 10. If I plot out their velocities, you see that it's moving very fast at 2, 6, and 10. So we didn't actually derive this yet. Let's go ahead and see where this comes from. The velocity of the points themselves. So again, remember the points themselves are not going to move left or right. They're going to just move up or down. So the velocity we're interested in is their velocity in the y direction at fixed x. So velocity, you may remember, is derivative of y with respect to t. And now we have to use this little bit of notation, which is the so-called partial derivative. So I'm going to write it like this, delta y over delta t, where this thing right here is called the partial derivative. We briefly talked about this earlier, but just as a reminder, all that means is we're going to take a derivative with respect to time, keeping x fixed. So the derivatives with respect to time, keeping x fixed. So if my y is a cosine omega t plus kx, I take a derivative with respect to time, that brings my omega out, and my derivative of my cosine is negative sine. So this is negative a omega sine of omega t minus k times x. That's my velocity in the y direction. And where will this be maximal? Where will this have a maximal magnitude? So the magnitude of this is just a omega magnitude of sine. And clearly the maximum will be when sine is equal to plus or minus 1, meaning the magnitude is equal to 1. So if we look, when is sine of this object equal to 1? Sine of the phase equal to 1? Well, that happens when the phase is equal to 90 degrees, pi over 2 radians, 270 degrees, 3 pi over 2 radians, and so on. If we go back to our drawing of the wave, here the phase is 0 because that's the maximum of the cosine. Here the phase is pi over 2 radians, 3 pi over 2 radians, and so on. And that's why those velocities are fastest at those points. All right? So the velocity is maximal when y is equal to 0, just like the simple harmonic oscillator. It's going fastest when it is going through that equilibrium point y equals to 0. All right. You can take another derivative. I guess I'll do that in a second to get acceleration. But first, let's do a couple of other conceptual questions. What is the wave velocity? When is the wave velocity largest? Point 1, 2, 3, 4, 5, all the way up to 11. So think about this for a second. Where is the wave velocity largest? And hopefully you got that this is a trick question. So the wave velocity is a constant. The wave velocity is always lambda divided by t. I can go ahead and solve for that. Or k divided by omega is another way to do it. So wave velocity, omega divided by k. When you plug in some numbers, that turns out to be 0.83 meters per second. And that's a constant. It does not depend on position. So at all of the points on this wave, they're all moving to the right at 0.83 meters per second. Finally, how long does it take for point 8 to go back down and up again? So remember, any given point in space behaves like a simple harmonic oscillator. If I'm simply able to get rid of this second term or set it equal to a constant, I just have a harmonic oscillator. And how long does it take a harmonic oscillator to come back to the same point? Well, that's the definition of the period. So the period, t, is 2 pi divided by omega. And when I plug those values in, that turns out to be 0.69 seconds. So there we go. That's the behavior of a very simple wave right here. Okie dokie. So now let's take the next step and do another derivative. We saw, when I started this problem, that velocity in the y direction is negative a omega sine omega t minus kx. Then since sine of omega t minus kx, if I flip the sign of that, I flip the thing in the sinusoid, I get a negative sign. You could also rewrite that as a omega sine kx minus omega t. We can take another derivative. So if I want to know the derivative of velocity with respect to time, that's going to give me my acceleration. That's partial derivative of Vy with respect to t. So again, I take a derivative, I factor out a minus omega, derivative of sine is cosine, and I get negative a omega squared cosine kx minus omega t. And what you may notice is this is simply negative omega squared times y. So acceleration in y is negative omega squared times y. Aha! That is the equation for a simple harmonic oscillator. So again, at any spatial point x, waves behave like a simple harmonic oscillator. Now the different thing that I can do with a wave is I can take a derivative with respect to x. So for example, I could take the derivative of y with respect to x if I say that y is equal to a cosine of kx minus omega t. And that's not too bad. I get a times k, derivative of cosine is negative sine, so I get negative ak sine kx minus omega t. I take another derivative. This derivative doesn't have a particularly interesting name, but it's going to be useful. And I get negative a times k squared times sine of kx minus omega t. So notice, this again looks a lot like a simple harmonic oscillator. The second derivative is equal to now negative k squared instead of omega squared times y. So the thing about traveling waves is that they act like simple harmonic oscillators in both time and space. So it's kind of periodic in both time and space. So here's that same thing written again. And that's really the defining property of a wave. That there's this relationship between spatial derivatives and time derivatives. So as a rewrite, if ay is negative omega squared y, and second derivative with respect to x is negative k squared times y, I can simply equate these two. I can simply solve for y and then equate them. And what you will find is that the second derivative of y with respect to time is equal to velocity squared times the second derivative with respect to x, where velocity there is precisely that wave speed, omega over k. So this guy right here that I've drawn in red, this is a big one. This is actually the single most defining property of a wave, this relationship between the second derivatives. And this equation itself is called the wave equation. So any material that satisfies this equation will give you waves at velocity v. And the thing that we are going to use is that this happens in strings. So for a string with tension F and mass per unit length mu, so mu is the mass of the string divided by the length of the string, the wave velocity will simply be given by the square root of the tension F divided by mu. Notice that I actually call the tension F in this part of the course to avoid confusion with T, capital T, which is the time period. Okay? So just be a little careful on that. I usually call tension F, and the velocity is the square root of F divided by mu. Okay, so for those who are interested, this is a really pretty derivation. It's quite nice. Uses a little bit of calculus, uses this technique we've done a few times in the after hours part, where you break up the string into a bunch of little pieces and then solve Newton's equations. But it's a little bit beyond the scope of this course, so I will do that in the notes and after class. What we do need to know is this is the equation for the velocity of waves on a string. Notice it's set by the physical constants, F and mu, which is what I said was true of velocity. One other thing you may need to know is that if I have a string, so if here's my piece of string and I kind of look down on it on the edge, so the string has a cross-sectional area A. Then this can also be written as the square root of the tension per unit area. So that's the tension of the string divided by the area, the cross-sectional area of the string, divided by the volume density, rho. Okay, so V is equal to the square root of tension divided by mu, or equivalently the square root of tension divided by the cross-sectional area A over rho, where rho is the mass per unit volume. These are equivalent expressions, but sometimes you might need to use one and sometimes you might need to use the other. All right, so let's just go ahead and get a little bit of practice using this with the following example. For those of you who remember the Little Rascals, I guess probably you're all too young, but hopefully one or two of you have watched old episodes. There are a couple of characters named Alfalfa and Spanky. So imagine they want to communicate by this old school method, which you've probably seen. These tin can phones. You have two tin cans. You have a piece of steel cable or something in between them. And what they're going to do, they're going to talk into one end. That sound wave is going to transmit through the steel cable, which you can just think of as a string under tension. And then it's going to come out at the other end. It's going to jiggle the other can, and as we'll see, that's going to create sound waves. All right, so these two cans are connected by a steel cable of mass 0.49 kilograms and length 21 meters. The question is, how hard do they have to pull on that cable in order to match the speed of sound in air, which is 343 meters per second? And what's the minimum tension required to avoid having a delay of more than half a second? All right, so take a minute, try to solve this, and then we will go over the answer together. Very good. So hopefully everyone's taken a shot at this problem. This is just an example to use that equation for the wave velocity. So as a quick reminder, this is waves on a string. And specifically for waves on a string, we have this nice new formula. The velocity of waves is the square root of tension F divided by the mass per unit length mu. All right, so what are we given in this problem? We are given that the mass of the string, the mass of the string is equal to 0.49 kilograms. The length of the string is 21 meters, and therefore we can solve the mass per unit length mu is simply m divided by L, or 0.49 kilograms over 21 meters. We don't know the tension in the string. That's what we're trying to solve for. But we do know what velocity we want. We want to match the speed of sound in air. So we want to pick a velocity equal to 343 meters per second. And now it's pretty straightforward to go ahead and solve for this tension. So I have V is equal to root F over mu. Let's take the square of both sides. V squared is equal to F over mu. Multiply both sides by mu. I get that my tension F is mu times V squared, which is mv squared over L. And when you plug in some numbers, this turns out to be 2,700 newtons. So that doesn't mean very much to most people. To give you a sense, the breaking tension of a steel cable is right around there. So this is approximately the breaking tension of a steel cable. Now, I don't know about you, but I have never successfully pulled so hard on a pair of can phones that I broke a piece of steel cable. So this is realistically never going to happen. They're never really going to be able to make the sound move as fast on the string as they would at the speed of sound. So, speed of sound in air, I should say. So part B of the question asks, what do I need to do if I want a half-second delay? All right? So let's say Spanky talks into one end. It takes half a second for that sound wave to travel along the string, and then comes out at the other end to alfalfa. So if there's a half-second delay over a length of 21 meters, what that means is that my wave velocity v is however far it travels over however long it takes. That's the length of the string over the amount of time delta t, which is half a second. And we can go ahead and solve for that. That means the velocity we want is 21 meters over half a second, or 42 meters per second. And again, we want to solve for the tension in the string. So I just go ahead and plug that in. My force is equal to mu v squared, now with v is 42 meters per second. That gives a much more reasonable number, about 41 newtons. So for comparison, if you actually weigh out the string, that's about 4.8 newtons. So already the weight of the string is giving about a tenth of this velocity. And if they pull on it a little bit harder, certainly they can avoid a half-second delay. So this is how waves travel on a string. And the important things that I want you to take away from this class today is that waves are excitations, are disturbances on top of a background. So waves are disturbances on top of an equilibrium. We describe them by this formula, y equals a cosine omega t minus k times x. I can also write that as a cosine omega t minus k times x. They satisfy the wave equation, which we wrote out, and the velocity is set by physical constants. So for example, on a piece of string, the velocity is set by the physical constants, tension, and mass per unit length, mu. All right, so that's all that I wanted to cover today that will be test eligible. For those who are interested, I quickly wanted to derive the equations here for the string. So for those of you who aren't interested, thank you for listening to this lecture. And for those who are interested, let's quickly talk about how we get this formula for traveling waves on a string. All right, so in order to do this, I need to solve Newton's equations. That's what's going to give me, of course, pretty much everything in this class. And the important things to do are to figure out how I'm going to treat a string, which is obviously a bunch of, it's a continuum of particles. All right, so the way I'm going to do that, which you may have seen a couple other times from my demos, I'll take my piece of string, and I'm going to break it up into little chunks. Very small pieces. And in particular, I will choose these chunks to be of length delta x in the x direction. Some very small length delta x in the x direction. All right? And I'll assume that in equilibrium, if I were not to do anything else, the string would just be flats of length L broken up into these little chunks of amount delta x. And when I do add a wave to it, I'm going to assume that the amount that any of them moves, y, is relatively small. In particular, what I really want when I mean that is that y is much less than, or the amplitude of the wave is much less than the wavelength of the wave. Okay? So relative to the wavelength of this wave, it's a very small disturbance on the string. And that's going to let me go ahead and solve the problem. So let's start near a particular point. Let's call it x equals 0 just for simplicity. It really doesn't matter. Now let's just call it x. May as well keep it general. All right, so I'm going to zoom in on some wave on the string. Here is my point x that I'm interested in. So that's the center point of this little chunk. And I'm going to consider 3 chunks. I'm going to consider that guy. I'm going to consider the one that's just over to the left. So it's centered at x plus delta x. And the one that's just to the left. That's centered at x minus delta x. All right. So here we go. I have these 3 little pieces. I know the mass of each of these 3 pieces. That's pretty straightforward. So the mass of each of these is simply mass per unit length, mu, or actually let me say this slightly differently. The mass per unit length of the string is the mass of each of these pieces, what I'll call delta m, divided by the length of each of these pieces, which is delta x. All right, so what that means is the mass of each of these little pieces is delta m, which is mu delta x. I also know the forces on it, so let's assume there's no gravity. What I'm going to do is I'm going to suspend the spring, for example, horizontally over the surface, so you could think of this like a guitar held horizontally. And I'm going to solve for the free body diagrams of this chunk in the middle. All right, so here is my free body diagram of that little mass in delta m. What forces are acting on that guy delta m? So the only force, if I neglect gravity, is the tension in the string. In particular, if I go over a little bit to the left, there's going to be a force which I'll call FL, pulling it to the left in the direction of the x minus delta x. Similarly, there will be a force pulling it to the right, F right. And the magnitude of both of these forces is just the tension in the string, because these are both given by the tension in the string. However, the direction is a little bit trickier, and we're going to go ahead and figure that out. All right, so we'll start about talking about this force on the right. I'm going to draw that out a little bit differently. So I'm going to draw my mass delta n as a little bead, a little circular bead, sitting at position x. And I'm going to draw my next object, also mass delta m, sitting at position x minus delta x. So the force of tension is going to act between these guys. It's going to act on a line between them. And if I draw this out, what I can do is I can define the distance between them to be delta y. In other words, if I know the position at x, and I know the position of x plus delta x here, I'm sorry, the guy that's just to the right, I can define the distance, the difference between those, as delta y. Y of x plus delta x minus y of x minus delta x, x. Right? So that's how far it is in the y direction. If I draw out a little triangle, I have some displacement y, like so, and some displacement x, like so. The angle here, theta, is pretty small. And we'll call this theta right to indicate that this is what's happening over on the right-hand side. So what I do know is that the tangent of that angle theta is simply going to be delta y, let's call it theta right, is delta y over delta x. And I'll call this delta y right to emphasize that this is the delta y over on the right-hand side. Or in other words, tangent of this small angle theta is y of x plus delta x minus y of x over delta x. All right, very good. So there are a few things that I can do here. One, by my assumption that this is a small angle, or sorry, a small amplitude of oscillation, this guy becomes a small angle theta. Kind of like we did in the small angle approximation for the pendulum. So for small angles, if I do the series expansions, sine of a small angle is approximately theta plus high order terms. So I'll drop those. And cosine is actually even easier. Cosine is 1 minus theta squared over 2. But if theta is small enough, I just forget about that next correction. So tangent, which is sine divided by cosine, is just approximately equal to that angle theta. Okay? So that is my angle. That's good. So if I know the angle at which this force acts, I can start to do Newton's laws, right? So here we go. Here's my mass delta M sitting at position X. And what I know is there's a force equal to the tension that is acting an angle theta r below horizontal. Actually, the way I've solved it, theta r is simply going to give me a negative value, the way I've drawn it. So that's good. And I want to break this up into components. In particular, I'm going to be interested in the y component. So let's go ahead and do that. Here's my tension, F. Here's my x component. Let's label these all FR to indicate that they're happening on the right hand here. Here's my y component. Here's my small angle theta right. And you'll notice that Fy is opposites the angle theta. So Fy on the right hand side is F times cosine of theta right. Sine theta right, because it's opposite. And again, I can appeal to my small angle approximation and say this is approximately equal to F times theta right. We'll leave that alone for now, but it's going to come back in just a quick second. And now I'm going to do the same thing on the left-hand side. All right? So that was on the right-hand side. I can do the same thing on the left-hand side. It's pretty straightforward. So here's my same thing on the left. There's a tension acting at a small angle theta left above the horizontal. And if you go through the same bit of algebra, what you can find is that theta left is approximately equal to tangent of theta left is approximately equal to sine of theta left. They're all basically the same thing as long as they're small. And it's going to be basically the same formula, except now shifted by delta x. So that will be y of x minus y of x minus delta x all over delta x. All right, so here's theta left, here's theta right, and now we are almost good to go. The last thing we have to do is to use Newton's laws. So as a reminder, the y forces on this guy are F theta r, acting roughly speaking down because theta r is going to be negative, and F theta left when I break up this component of theta left. So these are the two forces acting in the y direction. There are also forces acting in the x direction, which at leading order are just both given by the tension, so they cancel each other out. So the total force in the y direction is equal to F theta left plus F theta right. I should be a little careful. The way I've drawn it, you add these two together, you don't subtract them, because theta r is simply happens to be negative in this case. It's not that I am it's not quite correct. Did I do this quite right? Let me double check. Maybe let me try to do it in such a way that I will get a positive number for both theta left and theta right. There are various ways to solve this, but I'm going to go ahead and try to do this. So theta right is going to be this angle right here. And I want it to be positive when y of x is greater than y of x minus x prime. So I'm going to do this as negative y of x minus x prime plus y of x. Okay, so that'll be a positive number the way I've drawn it. Then fy is going to be pointing down as shown, so that'll be minus sign here. And similarly, theta left, I want to be positive the way I've drawn it. If y of x plus delta x is greater than y of x, so I'll do positive here, negative there. And when I plug that in, that's going to be now positive force, F theta L. So that's F theta L minus F theta R. So now let's go ahead and plug in the expressions we have. There's an overall tension which factorizes. Theta left is y of x minus delta x minus y of x over delta x. Theta R is y of x minus y of x plus delta x over delta x. Those are all the forces acting in the y direction at leading order in delta x. And that's equal to the mass of this object, which is delta m, times its acceleration in the y direction. Okay? So this expression is equal to delta m times a delta y. Let's go ahead and massage this expression a little bit further. So on the left-hand side, I have the tension F times y of x minus delta x. 1 second. Plus, I have a negative times a negative is a positive, y of x plus delta x, minus now twice y of x. Just be a second here. All divided by delta x. And so now what I'm going to do is I'm going to do a Taylor series expansion in the limit where x is small. So this is always a very useful technique. For example, let's do this guy right here, y of x minus delta x. So y of x minus delta x, if I Taylor series expand it around delta x equals 0, is y of x minus delta x times the derivative, y prime of x, plus delta x squared over 2 times the second derivative with respect to x, and so on. And similarly with y of x plus delta x, I get y of x plus delta x times y prime plus delta x squared over 2 times y double prime, and so on. Now when I add these two guys together, notice that what I get is 2y. The first order term cancels, 0 times delta x, and the second order term does not. So the second order term gives me delta x squared divided by 2 times 2 is nothing, times the second derivative. All right, so we can now go ahead and plug this back into our expression. We have tension F times 2y of x plus delta x squared times y double prime, plus higher order terms we're going to forget about, minus 2y all over delta x, and that is equal to the mass of the object, delta m, times the acceleration in the y direction. And aha, our two y's cancel out. So does one of our delta x's now. And I'm left with a very nice expression, f delta x times y double prime of x which I'm going to go ahead and write out now as a second derivative, second partial derivative, d squared y partial x squared, is equal to, that's the second derivative with respect to x, keeping time fixed. On the other hand side, delta m we said was mu times delta x times the acceleration with respect to y, which again is the second derivative of y with respect to t squared, keeping everything else fixed. So that's this partial derivative. And now we're almost done. We cancel out the delta x's on either side of the equation. We bring the mu over to the other side, so I have d squared y dt squared, that's all partial derivatives, sorry about that, is equal to f over mu times partial y, second derivative of y with respect to x. And remember, this was the wave equation. D squared y dt squared is v squared d squared y dx squared. So finally, we make the identification that the velocity squared is equal to f over mu, or in other words, the wave velocity in a string is the square root of f over mu. So the big take home for those of you who have been following these post-lecture calculus things, a very useful technique which engineers, physicists, everybody tends to use is break up your object into little pieces and then solve Newton's laws or conservation of energy or whatever formula you have in terms of each of the little pieces. It's very useful. The other thing that tends to work is small angle approximations, which is predicated under the assumption of a small disturbance, an amplitude much less than the wavelength of the disturbance. All right, so that's all I have to say today. Thank you for sticking it out to the bitter end. Have a nice weekend, and next week we will finish up waves and be done with the class. Thanks, bye.